welcome to another episode of NJ's Dojo. Today in the dojo, we will be talking about gravitation. Now, gravitation is a very important concept that most of us seems to distraught. Um, in our everyday life, we experience gravity all the time, and that's the sole reason why we keep in touch with the ground and make sure we don't, fly off. Imagine going into space, and as you see in the movies, people who go to outer space, since there's no gravity on celestial objects, deemed to fly off or float into midair. But now, because of gravitation, because of the Earth's gravitation, we are able to stick on the surface of the Earth and be able to comply with everyday things. Normally, gravitation is defined as a constant variable in each planet. So in planet Earth, gravity is simply equal to 9.8 meters per second squared. Gravity is also a form of acceleration since it's a type of force that actually exerts effort in order for a certain velocity of an object to move. Okay, so in a deeper sense, gravity also involves the idea of circular motion. So for example, we need to know lots of different concepts of circular motion, such as angular force, angular frequencies, but we'll tackle that in a much more deeper sense later. How gravity works is simply, for example, we have the Earth's surface. Of course, we all know that gravity is located at its center. And as we all know, the Earth moves in a circular manner. There. Now we must know that in a circular motion, each point of the circle entails a different type of free body diagram. So for example, I'm at this point. It's actually the velocity, the tangential velocity, we call that tangential velocity, is actually pointing there towards outwards of the circle in a form of a tangent. That's its tangential velocity. And we all know that the force applied on this point in time for the circle always points to the center of the circle, or the center of the mass, because of gravity. And it's the same for all points of the circle that constitutes to the revolution or the rotation of the ideal mass. Now basically, gravity is everywhere, and we need to understand this concept in order for us to truly grasp the idea of gravitation, or how circular motion compels society or everyday physics. Okay, another important component of gravitation or circular motion is the idea of centripetal acceleration. Basically, for a circular motion, the acceleration vector has two physical components. The first results from the change in speed and points in the tangential direction. So if I were to draw it clearly, a while ago we discussed how each point of the circle has different velocities and concurs to different directions. So as stated a while ago, the first component points to its tangential direction. Okay. And this stems to a second, which comes from the continuous change of direction of the velocity vector and points in the negative radial direction towards the center of the circle. Okay. As stated a while ago. Okay. However, this second component is present even if the circular motion proceeds at constant speed. If the angular velocity is constant, then the acceleration is basically zero. but the velocity vector still changes direction continuously as the object moves in its circular path. This is because that there is an acceleration that changes the direction of the velocity vector without changing the magnitude, and this is known as the centripetal acceleration. And this is defined in the equation A sub c is equal to velocity times angular velocity, or it would also be equal to velocity squared over radius of the circular object, or it could even be angular velocity squared multiplied by the radius. In order to give you a much broader idea of centripetal acceleration, let's try to manipulate acceleration. Okay, so for example, we've got this object, and let's say the circular motion is indeed accelerating. So that would mean, and that would mean that acceleration would be greater than 0. So of course, if you have the center, we have a point in the circle whose velocity will always point in its tangential point, and of course we have its another component that points to the center of the circle. Okay, now because of centripetal acceleration, we know that centripetal acceleration is always the acceleration pointing towards the center. That gives its name, centripetal acceleration. Centripetal, which means center seeking. So we know that AC acceleration, centripetal acceleration is here. And since the acceleration is greater than 0, its acceleration is also towards the acceleration based on tangential velocity. It's also pointing in the same direction of the velocity. Therefore, once from our previous lesson of vector addition, we know that acceleration would then be pointing here, which would cause a change in the magnitude of the speed of the object and also direction at the same time. So another example would be when the acceleration is simply equal to 0, or if the speed is constant. Now, because of centripetal acceleration, the circular path, the point in the circular path will always change direction. And okay, let me change so we've got A is equal to 0. So we've got the point in the circle, tangential velocity, of course the center, where the centripetal acceleration is pointing to. Now since there's no acceleration, so meaning it's at constant speed, only the centripetal acceleration will be the only acceleration present in the system, for it does not change the speed of the object, but rather simply the direction, and it's constant when it goes here. So for example, it's here. It's the same thing as the magnitude of this vector is the same as this vector throughout the circle because the speed is constant. And finally, we have another type of acceleration when it's less than 0. That would mean it's actually this losing speed or slowing down. So again, point in circle, center, so we've got the centripetal acceleration pointing to the center, and of course the tangential velocity. So we know that the acceleration will always point to the centripetal acceleration will always point to the center. And now this time, since it's actually slowing down and the acceleration based on tangential velocity is actually losing speed, so it points up the opposite direction there. And this is your acceleration based on tangential velocity, and that would mean the resulting vector would accelerate here with your final acceleration. And that's basically the idea of centripetal acceleration, and that causes mainly the change of direction of the circle of an object that would relate to the circular motion of the object. Okay, so let's try a problem revolving around centripetal acceleration. So if you want to generate 840,000 gravity, G means gravity, of centripetal acceleration in a sample rotating at the distance of 23.5 cm from the rotation axis, what frequency do you have to enter into the controls? What is the linear speed with which the sample is then moving? Okay, so first we have to draw our diagram. And we have to assess the situation because we know that we have the values for centripetal acceleration. We also have the values for the radius itself. So basically, we're looking for the frequency and the linear speed. Now, frequency is the number of oscillations at a given time. So basically we can relate that with angular velocity. Now, as we try to assess the problem, we should understand that centripetal acceleration is given by the equation AC is equal to angular velocity squared times radius. And again, as I mentioned, we can relate angular velocity with frequency because angular velocity is simply equal to 2 pi f, which was present in a previous video. So now we can plug in variables. We know that AC would then be equal to 2 pi f squared multiplied by radius. And since we're looking for frequency, we can derive the equation for frequency as frequency is equal to 1 over 2 pi multiplied by the square root of the centripetal acceleration over radius. Now that we have that, we can plug in variables. So frequency is equal to 1 over 2 pi multiplied by 840,000 times gravity, and most people would mistake G as grams, but for this case it's gravity, so we multiply it by 9.8 meters per second squared. Okay, and that's over radius, and since the radius is given as 23.5 centimeters, you have to convert it to meters in order to adhere to the protocols of the equation. So it would then be 0.235 thousandths, okay, meters. Okay, so now that we've got that, we can calculate frequency as 942 seconds to the power of -1, and that, as you convert it to RPMs, rotations per minute, that would be equal to 56,500 RPM. And basically that's how you get the frequency of the problem. Now the second question is asking for the linear speed with which the sample is then moving. And then we have to take into consideration the kinematics, the things we've learned before. So now we know that angular velocity is also equal to velocity over radius. So since we're looking for velocity, we can simply derive a working equation of angular velocity multiplied by the radius. And then from this from this equation, we can plug it in so that we can simply solve it as velocity being equal to 2 pi frequency multiplied by the radius. And this is the case because we know these values. We have the values now for frequency. We also have the value for radius, and this makes the solution much more easier. So now we simply plug in the variables. So v simply equal to 2 times pi times the frequency, which is 942 seconds to the power of -1, multiplied by the radius 0.235 meters. And once we try to calculate that, that would be equal to 1.39 kilometers per second. And that's how we solve for the linear velocity of the circular motion. Another important component of circular motion we have to tackle is centripetal force. Now, centripetal force is defined in the variable Fc. And the centripetal force is not just another fundamental force of nature, but is simply the net inward force needed to provide the centripetal acceleration necessary for circular motion. Now, the centripetal force in the circle obviously has to point inward toward the circle center. Its magnitude is the product of the mass of the object and the centripetal acceleration required to force it onto a circular path. So basically we know that centripetal force is equal to the mass times the centripetal acceleration. We can also define it as mass times velocity times angular velocity from the definition given by centripetal acceleration. And because of this, we can also derive it as mass multiplied by v squared over radius as we continue to substitute different variables into the equation. And from this, we can also manipulate it as mass multiplied by angular velocity squared multiplied by the radius. And these equations can work accordingly in order to find different components of the circular motion. So let's try to answer a simple problem. Suppose the vertical loop of a roller coaster has a radius of 5 meters. What does the linear speed of the roller coaster have to be at the top of the loop for the passengers to feel weightless? Now, a person feels weightless when there is no supporting force from a seat or any restraint acting to counter his or her weight. For a person to feel weightless at the top of the loop, no normal force can be acting on him or her at this point. So basically, if we draw this free body diagram, it would normally be understood that a person would be located here at the top of the roller coaster, and of course the center and the radius here. Okay, so when the person is on top, this person, basically the free body diagram of the person would be that the force of gravity would be acting upon here, and of course there will be a normal force acting upon the same object. But in order to feel weightless, as I said, there should be no normal force acting upon the object. So basically, the person has to be at its utmost force of gravity without the influence of the normal force. Now, how do we achieve that ideal? So, the force of gravity and the normal force acting on passenger in the roller coaster at the top of the loop are pretty much shown here. And the sum of these forces is the net force, which has to equal the centripetal force in a circular motion. If the net force, which in this case is the centripetal force, is equal to the gravitational force, then the normal force is 0 and the passenger feels weightless. So basically, we just have to state that the net force is equal to the centripetal force, and that the net force is the sum of the normal force and the force of gravity. So we basically declare that the centripetal force is equal to the net force, which is also equal to the force of gravity plus normal force. And for the feeling of being weightless at the top, n has to be 0. So just cancel that out. So basically, each one of these components basically equals to one another. So now we know that the force of gravity from our previous videos is mass times the value for gravity. And then for the magnitude of the centripetal force, from the previous slide we've tackled, we know that centripetal force is equal to mass times centripetal acceleration. And through that, since we need the linear speed of the roller coaster, we can use its derivation of mass times velocity squared over radius. Okay. So now that we've got that covered up, we can simply plug this equation into this equation, because we know that centripetal force is equal to force of gravity. So we can simply say that, let's add another line here. So mass times velocity squared on top divided by radius is equal to mg. Again, so as we play with the variables, we know that mass would simply be cancelled out, and we simply get a working equation of v is equal to the square root of radius times gravity. So with this working equation, we can simply get the linear speed of the roller coaster on the top of the loop for the passengers to feel weightless, since centripetal force is equal to force of gravity having no normal force acting on the object. So we finally plug in the equations. Let me use a different color. So now we're looking for v, and that's equal to the square root of the radius, 5.0 meters, multiplied by the force of gravity, 9.81 meters per second squared. Okay, so we get that velocity would be equal to 7.00357 meters per second, and since we're looking for precision, we can simply round it up. So velocity is equal to 7.00 meters per second. And that's how you get the linear velocity basing from centripetal force. Okay, now that we've tackled a lot of the basic concepts of circular motion, we are now ready to immersify ourselves in gravitation, specifically Newton's law of gravity. Now, Newton's law of gravity is basically the foundation of many gravitational equations. Okay, so up to now we have encountered the gravitational force only in the form of a constant gravitational acceleration. So we are very familiar that the Earth's gravitational acceleration is 9.8 meters per second squared. And we basically get gravitational force through multiplying that with the mass of an object on which the force acts on. However, there are many instances of defying gravity, such as seeing astronauts run or act on the moon. You notice that there's really lesser force of gravity present. And because gravitational force is different there, therefore the approximation we have used of a constant gravitational force depends on the mass of the object the force acts on. Cannot be correct away if the said action is not on the surface of the earth. The general expression for the magnitude of the gravitational interaction between 2 point masses m1 and m2, two different interacting masses or objects at a distance r is equal to the absolute value of the second radius minus the first radius from each other. This stems to the equation of force quantity r, or the function of the force of gravity in terms of radius being equal to a gravitational constant of g multiplied by the first mass to the second mass and the difference of the radius. This relationship is known as, again, Newton's law of gravity, and is an empirical law deduced from the experiments and verified extensively. The proportionality constant g is called as the universal gravitational constant and has the value to 4 significant figures, which means g is equal to 6.6738 times 10 to the power of negative 11 newtons times mass squared over kilograms squared. So let's try to answer another simple problem using Newton's law of gravity. Okay, suppose you live in the Midwest of the United States. You see the moon and the planet Mars. Your mass is 85 kilograms. What is the force of gravity on you due to the celestial objects? Okay. So of course, considering that the mass of the moon and Mars isn't given, we had to search for the values of these certain celestial objects. So the internet would say that the mass of the moon would be equal to 7.35 times 10 to the power of 22 kilograms. And the mass of Mars, of Mars is 6.4 times 10 to the power of 23 kilograms. Okay, so other than that, we also need to search the distance from yourself to the certain celestial objects. So distance of the moon to you is equal to 3.84 times 10 to the power of 8, and distance of Mars to you is 136 million kilometers. Or we can simply write it down as 1.36 multiplied by 10 to the power of 11. Okay, so now that we've got these lacking variables, we can now solve for the force of gravity on the two celestial objects acting upon us. So first we begin with the moon. Okay, but before that, we have to keep, since we're solving for two different celestial bodies and we're using the same equation for each, we have to take a stand or write the equation needed. So again, we know that the force of gravity is equal to a gravitational constant times the mass of the first object times mass of the second object. In this case, we will be using mass 2 as our own masses, multiplied by r squared. Okay, this is a correction from the previous example. Here in Newton's law of gravity, we have to put squared here. That's one mistake I've committed. Okay, so now that we've corrected that, we can now use it to solve this problem. So we have this equation and we have to solve these two the force of gravity for the moon and planet Mars using this equation. So for the moon, we have the force of the moon is equal to gravitational constant times mass of the moon multiplied by mass, like my own mass, divided by radius squared. So now we try to plug in variables. So the force of gravity of the moon, we know that gravitational constant is simply 6.67 multiplied by 10 to the power of negative 11, and multiply that to the mass of the moon, which is again 7.35 times 10 to the power of 22, and then we multiply that to our own mass, which is 85 kilograms, divided by the distance between the moon and ourselves. So it's 3.84 times 10 to the power of 8. As we multiply that, we get that the gravitational force of the moon acting upon us is 0.0028 newtons. Okay, so that's the gravitational force of the moon acting upon us. Now to solve for Mars, it's pretty much simple. It's just that you just simply change the variables. So now we've got this. We simply change it to F Mars is equal to 6.67, which is the universal gravitational constant, times 10 to the power of 11, multiplied by, since the mass of Mars is 6.4, so there we have to multiply it with 6.4 times 10 to the power of 23, and then we multiply that with our own mass, 85 kilograms, divided by the distance between planet Mars and us, which would be 1.36, times 10 to the power of 11. Now, as we multiply for that, we get that the gravitational force of Mars acting upon us is simply equal to 2.0 times 10 to the power of negative 7 newtons. And basically, using Newton's law of gravity, we can get the different forces of gravity acting upon different objects beyond the surface of the Earth, and not just the Earth itself, and using the gravitational constant of 9.8 meters per second squared in order to get the force of gravity. Because of this law of gravity, we are able to get different types of forces of gravity from different celestial objects, not just the Earth. Okay, now that we've covered up Newton's law of gravity, another important topic we have to discuss in order to understand gravity is gravitational potential. And just like any other energy types, potential energy is the storing of energy for later use. This holds the same for gravitational potential. Now, gravitational potential that states that the gravitational potential energy of an object is proportional to that object's mass. When we employed energy conservation to calculate the escape speed, we saw that the mass of the object cancelled out, because both kinetic energy and gravitational potential energy are proportional to an object's mass. Thus, the kinematics are independent of the object's mass. For example, let's consider the working equation in order to figure out the Earth's gravitational potential energy, which is defined as V in terms of R, which is equal to negative gravitational constant times the mass of the Earth divided by radius. Now, because of this working definition, this definition has the advantages of giving information on the gravitational interaction with the Earth independently of the other masses involved. And eventually, we can use this and multiply it to another mass in order to figure out how this mass interacts with the Earth's mass. This equation is immersively explained in detail later on in electric potentials. Okay, so now that we've tackled a bit on gravitational potential, let's try to solve a problem. A small spherical moon has a radius of 6.30 times 10 to the power of 4 meters and a mass of 8.00 times 10 to the power of 18 kilograms. An astronaut standing on the surface of the moon throws a rock straight up. The rock reaches a maximum height of 2.20 kilometers above the surface of the moon before it returns to the surface. What was the initial speed of the rock as it left the hand of the astronaut? So basically, we can draw a simple diagram on this just to see how the problem is played out. So we simply have to know that if this is your y value, your rock is thrown upward and it reaches a height. Basically, this height is its highest point on its straight line trajectory. So now, we know the mass and the radius of the moon, and this allows us to compute the gravitational potential. Knowing the height that the rock attains, we can use energy conservation to calculate the initial speed of the rock. Okay. So as we use the previous equation we've tackled on the previous slide, we know that the potential energy of the function of the potential energy, gravitational potential energy, are simply gravitational potential in terms of radius is equal to negative g, gravitational constant, multiplied by the mass of the moon of the environmental object divided by the radius of the moon and we multiply to the mass of the rock. So we denote M as the mass of the rock, M moon as the mass of the moon, and R moon as the radius of the moon. So now the potential energy at the top of the trajectory is basically adding more to its radius. So that means the function has to change from the gravitational potential R moon plus H. That's a plus sign, sorry, and this is an H. Let me just erase it. Okay, H is equal to basically the same equation, but we simply add H, since the rock was thrown upward. Okay, so aside from that, since we're using the conservation of energy to solve this problem, you should also note that the kinetic energy based on, in terms of our moon, of the radius of the moon, is equal to same equation as before, 1/2 times mass times velocity squared. Okay. At the top of the rock's trajectory, which is K R moon plus H, which is the height, obviously the kinetic energy is 0 because as from the previous video, we know that energy is conserved, and since at this point the rock is at its highest displacement, that would mean all energy is stored, and the gravitational, and it's known as gravitational potential, since eventually at the point after that point of time it will immersively go back down to the surface of the moon. Okay, so now we can identify, we can manipulate the conservation of energy equation. So it would be potential energy of our moon plus kinetic energy of our moon is simply equal to the potential energy of our moon. Let's just write radius. I'm sure it's understandable that it's the radius of the moon to save time. So radius plus maximum height, okay, plus kinetic energy based in terms of radius plus height. Okay, so now we know that, we can simply plug in the variables needed. So we know that this is basically this, so negative gravitational constant, mass moon. Okay, so to make things simpler, I'm just going to make R as radius, R moon, and capital M as the mass of the moon. Okay, so let me try to erase this. Okay, here we go. So we've got negative gravitational constant times M, mass of the moon, times radius, times the mass of the rock, plus 1/2 mv squared is equal to negative gravitational constant times mass of the moon over radius of the moon times radius of the moon plus the height of the thrown rock times mass of the rock. And now, since again this has to be 0, since At this point in time, the rock is at its highest point, so all energy is potential. So this is 0. Okay, so now we try to manipulate the equation. Since we're looking for the initial speed of a rock as it left the hand of the astronaut, we're simply looking for this v. So as we rearrange, there are some variables that get cancelled out, so we inevitably end up with the equation velocity times 2 times gravitational constant times the mass of the moon multiplied by 1 over radius of the moon minus 1 over radius of the moon plus the height. Okay, so now that we've got these variables, we can now substitute everything we've got based on the question. So since we need more space, I'm just going to maybe delete, just take this out. Wait, sorry. Okay, solid color. Okay, we just try. Oh, outline. Okay, no outline. Okay, I'm just going to take that out. Unnecessary. Okay, but I'm not going to take this equation out because that's the equation we actually need. So now I'm going to type it in. Now I'm going to plug in variables. So v is equal to 2 multiplied by gravitational constant 6.67 times 10 to the power of negative 11 multiplied by mass of the moon 8.00 times 10 to the power of 18 multiplied by 1 over 6.30 times 10 to the power of 4 plus the same thing. Let's put a bracket here to make it more specific. 1 over 1 over 6 point, let me erase that, 6.30 times 10 to the power of 4 plus the height of the thrown object, 2.20 times 10 to the power of 3 meters. Okay, so once we calculate that, we inevitably get the velocity being 23.9078 meters per second. And that's how we get the initial speed of the rock as it left the hand of the astronaut. Finally, the last thing we will discuss in gravitation for this tutorial is Kepler's law. Now, Kepler's law is a very important notation in the field of gravitation because it deals with the planetary motion and how gravity plays in our solar system. These laws were discovered by Johannes Kepler and use empirical observation mainly from data gathered by Tycho Brahe and sophisticated calculations to arrive at these famous laws. Now, basically, these laws were published decades before the birth of Isaac Newton, whose law of gravitation would eventually show why Kepler's laws were true. And basically, this is significant because it prevailed a worldview at that time, with the Earth being the center of the universe through the geocentric theory. Now, basically, these laws are founded upon 3 types of laws. The first law deals with orbit. The second law deals with area. And the third law deals with periods. Now let's try to get an in-depth idea on these types of notions. Okay. Oops. Okay. So the first law states that all planets move in elliptical orbits with the sun at one focal point. So if we were to draw this, okay, if we were to draw, let's say this is an orbit. An orbit is deemed by Johannes Kepler to be an elliptical path. And since the sun is at the focal point, it's not necessarily a circle but instead an ellipse. So let's say if this is the sun and this is a planet. So a planet revolves around the sun in an elliptical orbit. So there are many parameters used in describing ellipses and elliptical orbits. So for example, the radius of this is one radius from the planet to the sun, and the other radius does not connect the planet or the sun, but instead the planet to a second focal point. We all know that the sun is the first focal point, and the second point is what radius 2 connects the planet and the second focal point. Now focal point 1 and focal point 2 are separated by 2c, and that's a distance, and when you cut this into 2, there will be 2 equivalent c's. Now for each point, in the first law of Kepler, it deems that the first radius plus the second radius is equal to 2a. And what is 2a? 2a is actually the width of the elliptical orbit, while b is the vertical component or length of the elliptical orbit. Inevitably, because of this, we now claim to have the perfect equation for ellipses, which would be x squared over a squared plus y squared over b squared, which equals to 1. And because of this, we now know how to solve for different components of ellipses, not just only for elliptical path of planetary movement, but also elliptical shapes of every physical quantity in our entire world. So another law deals with areas. Now areas is what compromises Kepler's second law, because he states that a straight line connecting the center of the sun and the center of any planet sweeps out an equal area in any given time interval. So for example, we have a circle. Then again, this is the sun. Let me write, okay. Whoa, it's okay. Here you have the sun. Okay, so basing from the previous law, let's say a planet is here and a planet is here, and of course, let's say we have the planet's radius is here for a certain period of time, and then eventually it proceeds here, basing from the focal point. Okay. Okay, so this is at the initial time, then eventually the planet moves to another position in a point in time. So basically this comprises of one area. So basically it's true if it happens here. If the planet is here and the planet moves here, for as long as the time is the same, the area is basically the same. So that means if this is area 2, this is area 1, area 1 will always be equal to area 2. Now in this diagram, in this diagram, it's not that appreciated. I mean, of course, it will be equal because it's at the center. So let me draw it in terms of an ellipse because I simply drew it as a circle. So let's say the sun is over here, and a planet moves from here to here. That it's given that the time is simply equal to 5. Let's say 5. Let's give a random value. Okay, so we have this area. Another goes for here. If a planet is at this area and it moves to this area, for as long as it's 5 seconds, area 1 will always be equal to area 2 for as long as the time interval is at constant rate. Now the third law of Kepler's law is one of the most important laws because its formula can be used in different types of concepts in the field of gravitation. Now this involves periods. This Kepler's third law states that the square of the period of a planet's orbit is proportional to the cube of the semi-major axis of the orbit. So which would mean that the square of a period over the cube of A is indeed constant. This proportionality constant can be expressed in the terms of the mass of the sun and the universal gravitational constant, which would mean T squared over A cubed is equal to 4 pi squared over gravitational constant multiplied by the mass of the sun. Now, in order to be more idealistic in periods, let's try to solve a problem on this. On November 14, 2003, astronomers discovered a previously known object in part of the Kuiper belt beyond the object orbit of Neptune. They named this object Sedna. The average distance of Sedna from the Sun is 77.6 times 10 to the power of 4 kilometers. How long does it take Sedna to complete one orbit around the Sun? Okay, so we can use Kepler's law to relate Sedna's distance from the Sun to the period of Sedna's orbit around the Sun. So for example, so we can relate the orbit of Sedna to the known orbit of the Earth using Kepler's third law, which was T squared, which we will take from the Earth's period over A cube of the Earth. Remember, A here signifies the radius of the orbit. Okay, so we equal it to squared Sedna, the period of Sedna over the radius of the orbit of Sedna. Because this holds true for basically every celestial object, because this is proportionate to all of celestial objects. So now, since we're looking for the period or how long it takes Sedna to complete one orbit around the Sun, we have to take into account this variable. So we can simply rearrange the equation to form Sedna times T Earth multiplied by A Sedna over A Earth. And because of the exponents, this has to be raised to 3 over 2. So now we plug in variables. T Sedna would be equal to So it takes 1 year. 1 year for the Earth to revolve around the Sun. So basically that its value for the period of the Earth. So now the radius of the orbit of Sedna is 77.6 times 10 to the power of 4 kilometers. And since it's known that the radius of the orbit of the Earth is 0.150 times 10 to the power of 9, we can simply plug it in. And once we try to solve this equation, we get the answer of 12,018 years. So we round it up to significant values. That would be T Sedna. It would take Sedna to orbit around the Sun basically 1.2 times 10 to the power of 4 years. And that's how you use Kepler's third law in order to answer different questions revolving around planetary motion. So that's it for today for the dojo. Please continue to look through different tutorial videos to learn about the ideas of physics and its concept revolving around human society. So basically that's it for today. Thank you so much. Good day.